We have obtained the formulas for energy release rates, constant force loading, this equation, 12F squared A squared in the numerator, and constant displacement loading. And when energy release rate reaches the critical value, fracture occurs. But is that fracture stable or unstable? That's the question we will examine in part B. And again, we can consider these cases separately. Constant force loading. The first case. What's the constant force loading? Its expression is already given. Let me write it one more time. Or I can copy it here. This is for constant force loading. Twelve F squared A squared B squared EH cubed. I plot this. Generate a plot of G. Suppose that it is G versus A. Then. Now, and furthermore, assume that resistance to fracture is R. R is resistance to fracture. Crack length is A. So, shortened crack in the specimen. G is proportional to A squared. Now, if you plot G versus A, you get a curve like this. Does fracture occur here for this crack length? G is less than R. Now, for F is less than F critical and fracture does not occur. Now, if you increase the force further, you get this curve. And at this point, for this crack length, fracture occurs, and F is equal to F critical here. Another observation, once fracture occurs, G remains larger than R, thus fracture is, what can we say about fracture process? Is unstable in this case. Crack propagation occurs without limit and the specimen fractures. How can I find F critical? In this quantity F critical. That's right. Yes. 12 F critical squared A squared over B squared EH cubed equals R. In other words, I have a formula for F critical B squared E H cubed over 12A squared or square root of this quantity. gives you critical. Difference between G and R becomes larger and larger. There is nothing to stop this propagation process, and fracture process is unstable in this case, or constant force load. Now, constant displacement type of loading. Second case. Constant displacement loading. How can we plot it? Or you can show G versus A again. G axis and A axis. It's G versus A. That's constant resistance of material. And suppose that this is the crack length in the specimen. I can plot G versus A. It's proportional to 1/8⁴. I can copy this again. This is our expression for G. For constant displacement loading. It's proportional to 1/8⁴. So therefore, you manually plot it, you'll find curve like this. Does fracture occur in this case? Does not occur. V is less than V critical. However, if you increase V, you'll be able to generate a diagram like this. Now, does fracture occur in this case? Yes. Yes, fracture occurs, V equals V critical, second case. And what can you say about stability of fracture? Is it stable or unstable? Stable, because G is less than R as soon as crack starts propagation. G drops and becomes less than R. As the crack grows, thus fracture is stable. And how can we find critical V or V critical? How can we find critical value? Yes, same approach, that's right. Equate these. G equals R is the fracture criteria. And CEH cubed over 16⁴ V critical squared equals R. And we can find V critical. It's 16 a to the 4th or 3EH cubed R square root of this quantity is critical V. However, stability is completely different. When G equals R, crack grows a small amount and stops at that point, unless you further increase the value of V. That's called stable fracture of the specimen. And it could be useful in experimental studies because it gives you a certain degree of control on crack propagation process that is stable fracture. Any questions about these results? We have mentioned that the level of energy available for fracture is the same for constant force and constant displacement loads, or for any loads for that matter. We can prove it if we introduce the concept of compliance. And I'll talk about it. This discussion will be on energy release rate. But this time it's going to be in terms of compliance of the specimen. Again, we can examine the cases separately. Case 1, constant force, loading. General expression is derived. G is F over 2B dV dA F. Compliance can be defined by considering the total deflection of the specimen, that's V. V equals C times F. And C is called compliance of the specimen. And this compliance is also a function of crack length. Compliance is a function of crack length. That's an important variable used in various computational methods as well. You can plot it as a function of A, or you can carry out certain computations regarding. It increases as crack length becomes larger. Material becomes less stiff and compliance increases. Now I can evaluate this derivative using this relation for constant force loading dV dA. Or evaluate just dV dA. Let's evaluate dV dA. dV dA is derivative of this product, C times F. Both are functions of A in general. This is dC dA F plus C times the FDA in general. But for constant force loading, is it equal to what? The FDA. The FDA is 0. And once you make this assumption, this becomes constant for constant force. Let's say that dVdAF. Therefore, dVdAF is dCdA times F. And we are going to substitute it into the expression of energy release rate shown here. This leads to G equals F squared over 2B dCdA. Energy release rate in terms of compliance. And I can follow a compliance approach for constant displacement loading. This is the result for constant force loading. Evaluate this case 2 for constant displacement loading. We start with the original expression. Let's go back and find it. G it's given here is G for constant displacement loading. Constant force loading is covered. It's for constant displacement loading. Again, you can start with this definition. V equals C times F total deflection, or the VDA is the CDAF plus C times the FDA. For constant displacement loading, dVdA is 0, no change in dVdA. And for simplified as, I'll rewrite the FDA. The FDA for constant displacement loading is minus F over C dCdA. We will use it with this form shown as the first equation. Substitute here and you'll find G as minus 1 over 2B V over C F dCdA. And 2 minus signs, so this is canceled out. This is G. V over C is equal to What is V over C? It's F. And we are ending up with exactly the same result. G is F squared over 2B dCdA. It's fun. This is for constant displacement loading. G equals F squared over 2B dCdA. And this is for constant force loading. G equals F squared over 2B dCdA. Well, energy available for fracture cannot depend on subsequent loading conditions. Same G is calculated. And in general, therefore in general, G does not depend on. Let's rewrite this part here, cancel this. In general, G does not depend on the subsequent loading conditions. That's an important result in fracture mechanics. G is used as a fracture parameter, and it's possible to change it in terms of compliance, as you see here. Any questions about these results? Now we can generalize our fracture criteria by considering crack stability. By accounting for stability of fracture process. Critical load required is determined by G equals R. And stability of fracture is related to the change, rate of change of G and resistance R. If the GDA is greater than the RDA, what can you say about this fracture process? G is increasing. Yes, it's unstable. It's going to be an unstable fracture process. And the GDA is less than the RDA. What's our conclusion? What can I say? Yes. stable next time. And there could be this possibility the GDA equals the RDA. This is called neutral equilibrium point. Fracture continues under neutral equilibrium. For this, if that's the condition for a given crack length. And this generalizes the results regarding energy release rates. And we will probably, not next week, but the other week, find the relation between energy release rate and stress intensity factor. Now for this criterion, G equals R is actually equivalent to stress intensity factor criterion. Any questions about these results? Yes, that's an important point. You can use finite element method to find C. You can be given a specimen. That is one of the ways, and you can give any kind of specimen. There are different specimens as well. Let's say that we are talking about a different kind of specimen. And it's a crack here. You load it, suppose that. And what's the mode of loading here? But it's also mode 1. There's also mode 1. I can find compliance. And once you, this is crack length, let's say that's crack length. And once you know the compliance, you'll be able to use the formulas derived to determine the stress test factor or energy release rate, or for the original specimen. Or any other type of specimen. If you know the expression of compliance by finite element method, you can find compliance. And then you'll be able to compute energy release rate as well. That's compliance method to find energy release rate. That's right. I'm going to give another example on calculation of energy release rate. Another case. Derive the expression of G for the double cantilever beam, DCB specimen, shown. We are considering same specimen with a different loading condition. It is again the same type of specimen. It's A. I suppose that you have distributed load stress acting on these surfaces. Sigma. I find energy release rate for this type of specimen. Again, this is a certain thickness. So that's the specimen. Thickness B, total length 2H. That fourth type of load or stress. I'm going to assume you have constant force type of load, constant stress type of load. And our original formula, recall the formula is derived for energy release rate. We also have a formula in terms of total strain energy. 1 over B du EdA under constant force. It can be shown that exactly the same form can be used for constant stress loading. G is therefore 1 over B du EdA sigma. I'm replacing F by sigma. It can be shown. But we will use this form. And this is now in terms of strain energy function. Energy rate for constant force condition. I can calculate total strain energy for this specimen, again, by considering cantilever beam assumption. Consider one of the beams or one of the arms here. Suppose that this is the upper one. And this is cantilever. Constant stress sigma. And thus the length is A. That's one of the arms. I'm going to find strain energy. Strain energy in the beam under bending, or strain energy due to bending. How do you evaluate strain energy? You can recall from strength of materials or machine elements. I'm going to place a coordinate system here. Let's say that this is X. Again, from strength of materials, strain energy, total strain energy is integral from 0 to A m squared over 2 EI dx. Here, contribution to UE due to shear force is neglected. That's an approximation. And we assume that contribution because of bending moment is dominant. And you will evaluate this integral, evaluate or calculate the bending moment in the beam, draw a free body diagram to be able to express the bending moment. And this is the beam under this stress, sigma. It is now x. And there's a shear force here, V, and a bending moment, which keeps this in equilibrium. M. M can be found using by equating the moments about this point, for example, A. Moment due to stress. Resultant force is sigma x times B. Sigma xb. B is the width. Moment time is x over 2. Therefore, sigma xb times x over 2. Resultant force times moment r. Or we will place this as sigma b over 2 x squared. Substitute into the integral. For total strain energy, m squared over 2 EI, and find separate the constants. You'll get sigma squared b squared over 8 EI times integral m squared gives x to the 4th dx. Such an integral. Compute this integral and you'll find UE for a single beam for one of the beams. So I'm placing the subscript B. This is for one of the beams. And you get sigma squared B squared a to the 5th over 40 EI there are two beams. Therefore, total strain energy UE is 2 UBE, which is sigma squared B squared a to the 5th or 20 EI. Once you know UE as a function of crack length, you'll be able to evaluate energy release rate. G is 1 over B. Du EDA. Constant force condition. Differentiators with respect to A, you'll get a to the 4th over 4 here. And or you'll get sigma squared B a to the 4th over called EI. And simplifying, even in this form, 1/12 EH cubed. G becomes 3 sigma squared A to the 4th EH cubed for this specimen, for this loading. And what can I say about stability of fractals? Suppose that R is constant. Yes, unstable fractal. We increase sigma, and at a certain point, fracture occurs. And once crack starts growing, it will not stop, and the specimen is going to be fractured. This is referred to as unstable. Unstable fracture process. I can show it on a diagram, actually. Again, G versus A. R is constant. And this is the variation. And we observe that G is always greater than R. Now, this is unstable fracture process. Any questions about this result? This is the end of the lecture for today.